My name is Jim Coplien, and I'm here from Denmark. It's my great pleasure. This is my second session this conference. I gave a tutorial on Tuesday on something called data context and interaction. And it's a paradigm, a way of thinking about programs that takes its cue from Alan Kay and his model of what objects really are. And his vision is of a network of interacting objects working together to solve some problem. And so I've been thinking a lot about networks, and for my entire career have been fighting the dragon of hierarchy and the dragon of classification, as well as the dragon of encapsulation. And I come here, and I have found now where the dragons have found a new home. So I found a bunch of people who treasure encapsulation for its own sake, and who tend to organize things in pure hierarchies. And I haven't heard the term network of interactions once here, but I have seen a lot of hierarchies. And so a lot of my work, and this is work I did together with Dr. Liping Zhao from Manchester University, is work on looking at what does symmetry mean in systems. Now, how many of you are patterns people? Yeah, well, what in the hell does that mean? What is a pattern? So in normal design, we tend to believe in symmetry. And we tend to even talk about beauty as being tied to symmetry. The beauty of a person's face is how symmetric they are. No. Nothing in nature is symmetric. And where beauty comes from, according to Christopher Alexander, who's the pattern guy, is from what we call local symmetry breaking, broken symmetry. And so in a symmetric system, you cannot faithfully model nature or create a reality that is faithful to the kind of laws of nature that your end users expect. And kind of to give you a foreview of where I'm going to go with this, is that most of the practice I see in domain-driven design is purely hierarchical, purely symmetric. And this leads to accidental complexity that precipitates from the act of applying domain-driven design to domain analysis. Now, I haven't run into anyone in this community yet here at this conference who really seems to appreciate domain analysis. But it's much older. This goes back to Jim Nabors in 1968. And there seems to be almost no intersection between this community and this many years old domain analysis and domain-driven design community. There's nothing in the literature that cites this stuff. And so, there's two communities around that are using this term, domain analysis and domain-driven design, with very different agendas and very different foci. Now, that community, which includes people like David Parnass and Jim Nabors, who I don't think is around anymore, they did understand this notion of multiple hierarchies and of complexity. Complexity, probably some of you at some time in your career have done top-down design. You build a hierarchy, either of a domain or of classes, that's called an inheritance hierarchy, or of functions, that's called a procedural hierarchy. And now I get negative points for pronunciation. In Canadian, these are simple or at best complicated systems. They are not complex. So a hierarchy is tantamount to being a complicated system, not a complex system, let alone a chaotic system or disorder. So I think it would get beyond complicated, which is the ability to take something apart and put it back together, and get truly in the realm of complex, that domain-driven design works against us. And Liv, almost as a footnote, in her keynote here a couple of days ago, said this kind of after, I think it was in one of the questions, about, well, you really can't plan this stuff in advance. You have to dive in and do stuff. I have a slight disagreement about that. We can use domain knowledge. But I still think the general underlying principle is clear and important and true. And what I want to do is kind of give you a tutorial on how we can talk about complexity from these perspectives from a mathematical point of view, based on symmetry. So most of us kind of understand geometry. There was this beautiful talk here this morning about the physics of software. And a lot of it resonates, I think, with the things I'm going to say here. And that a lot of physics is about understanding the geometry of things. Or we use geometry as a language for talking about physics. And you're going to see a little bit of physics in my talk, too. And a little bit of biology. So here's Charlie. Charlie and my friend the starfish. How do you know it's a starfish? How does your mind know this is a starfish? Well, he has a certain geometry. Now, what is the classification you hold in your mind of what a starfish is? Well, there's certain invariants that hold across all starfishes. They're true of all starfishes. And what it is a set of invariants that remain the same under the possibility of change. So we can draw a line through Charlie, and we can rotate him, and he still looks the same. So there's a vertical axis of symmetry. That rotation that we just did is a function. You can write it as a mathematical function that transforms Charlie 360 degrees around that axis, or any number of degrees around that axis. And that's a function. So we have that function. We're going to put it in a set. Now, there's a bunch of other functions, too. We can rotate Charlie about any of these axes, and Charlie looks the same. So Charlie has a 5-fold symmetry, and this becomes his geometry. So if we rotate him among any of these axes, and he still looks like a starfish, which is the invariant, then these functions together form a set of what are called structure-preserving transformations. And this is a word the pattern people will recognize. This is a term that Alexander uses, because Alexander was also a mathematician who had studied group theory. And oh, by the way, a group also has to have, every function has to have an inverse, and there has to be an identity. And if I put all these into a set, it's called a group. It's called a symmetry group. So we have this mathematical set, which is the symmetry group of Charlie. And oh, there's a few more. I mean, we can rotate Charlie that much, or that much, or that much. And these functions go in that group as well. So the collection of all these things define what Charlie is as a starfish. And I put them all in a set, and together with this invariant, which is Charlie looks like a starfish, and an identity, and all these things having inverses, we have the symmetry group of Charlie. And this is what geometry means. Geometry and symmetry are isomorphic, or at least homomorphic to each other mathematically. So this is called the symmetry group of Charlie. And they have a lot of nice properties, like associativity, closures, inverses, and identity, all under some invariant. You think of invariants in programming, right? You have a base class, and it has a method called x. And I have a derived class, and it has a method called x. What must be invariant around those methods of x? Well, the precondition of the derived class has to be at least as strong as the preconditions for the base class x. And the postconditions can be no weaker. Do I have this right? I mean, this is basically the list called substitutability principle. It is a symmetry. How about procedure calls? Every time I call a procedure, it has the same types of arguments. I get a different activation record every time. So procedures are a symmetry. So every programming language feature that you can think of is a symmetry. And so we can formally define symmetry, and no, I'm not going to really go into these mathematics. This is more to scare you and impress you. But this is a classic definition of symmetry for geometry, where, X is a line or a plane or some space, and, A is in the set of X. A symmetry of A is an isometry, meaning same measure, invariant, that maps some X onto X within T, which leaves A invariant. And so this set is called the symmetry group. Now, something key here is there is no symmetry without asymmetry. The two go back and forth, hand in hand. And that's kind of why I put up this title slide, which with the color rendition of the projector doesn't look very good. But if you look very carefully, how many of you see the hourglass? How many of you see two faces? Well, they're both there. Classic kind of puzzle picture. And I mean, there's a symmetry-asymmetry thing going on here. Oh dear, yeah, I have to go through these animations again. Sorry for that. So these notions of symmetry govern how we as human beings see things. And by the way, your minds love symmetry because it's efficient. So when I remember you tomorrow as the person who was sitting here in the front row, I'll only remember half of you. Because my mind takes half of you, remembers it in my mind, and then it will construct the other half from that half as a way of kind of saving cells. And so the brain loves efficiency. And that's one of the reasons we love DDD. Because DDD is a symmetric worldview. It divides things into sets that are disjoint. It divides things into hierarchies. And I mean, I've been carefully watching the talks here, and I'll have an example from Vernon's talk here this morning. It was a classic example, makes a classic mistake of believing that the world is hierarchical, and that we can hierarchically derive subdomains from the superdomain. And it's kind of the cultural expectation, and it's how we talk about things as people, because we make oversimplifying assumptions about how the world is structured based on our experience. And in dialogue, we have to make some approximations. How many of you have read Thinking Fast, Thinking Slow? So, I mean, we all have this system one brain that has to make snap judgments, and it's largely based on seeing things as symmetries, because our mind can react with those very, very fast. To deal with broken symmetry requires system two. It requires deep thinking and looking beyond this. Now, there's also something called class-oriented programming. How many of you have done object-oriented programming? When's the last time you wrote an object? Now, JavaScript people, you can keep your hands up. Because Smalltalk is a class-oriented programming language. It was destroyed in, 72, 76? Object-oriented programming language, yeah. Back in the 1970s. By the time it came in Smalltalk 80, it had been destroyed. And that's why we're in the mess we're in today. It's largely because of Simula, Smalltalk, and then C++ institutionalized it. And you can just read Dick Gabriel's essay, Worse is Better. C is the ultimate computer virus. And C++ is kind of its cousin. It's allowed us to think that we're doing object-oriented programming. It's not. It's class-oriented programming. And it tends to be purely hierarchical. I mean, multiple inheritance in C++ just doesn't work. It just has the wrong semantics. I won't go into the example. So what does symmetry mean in software? I mean, human minds love symmetry. It's very efficient. How many of you recognize this? If for each object O1 of type S, there's an object O2 of type T such that blah, 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 blah. Anyone recognize this? What is it? That's the LSP. This is the OOPS law definition of object-oriented programming. It says it's based on a symmetric relation. Ooh. This looks kind of similar, doesn't it? So the formal definition of symmetry and the formal kind of OOPS law definition of object-oriented programming are very, very similar. And they're based on this notion of an invariant, which is sometimes called the Liskov invariant, or sometimes called preconditions and postconditions, or the class invariant. These things are pure symmetries. So this is subtyping. Inheritance is also a symmetry. Function calls are also a symmetry. Template instantiation is a symmetry. Declaration, instantiation, loops. Loops are a special kind of symmetry that in physics are called spiral symmetries. And so if you look at the programming languages that are elegant, pure, beautiful, like Lisp and Smalltalk, they express symmetries. If you look at the languages that have survived, that grow, that are accepted, they're messy as hell. Like C++. It has unions, private inheritance, overloading, template specialization. I mean, all of these are, who thinks up this crap? But it's necessary to have these are perfect broken symmetries with minor changes to the symmetric axis that are necessary to express the complexity of the domains that we are really in. If you have a model that incorporates this broken symmetry, which DDD does not. So there's a lot of, this builds on a lot of system one thinking we have, a lot of beliefs. So here's a drop of milk coming from a carton of milk, and it's going to splash in this pool of milk. So I'm going to get a perfect rim around the edge, right? The initial system is perfectly symmetric in a rotation basis, right? Like Charlie was, as a starfish, I could rotate him. I can rotate the system and it's symmetric. The drop is symmetric, the pool is symmetric. I rotate it, it looks the same. So Curie's law, named after Madame Curie, says that every symmetry of the result is a symmetry of the cause. So when this drop comes down, I'm going to get a perfect rim of rising milk around the edge, right? Uh-oh. It's not a perfect rim. The symmetry breaks. This is how nature works. By the way, do you know it's always a multiple of 12 droplets? Spooky as hell. You are an instance of originally a single cell with DNA that grew and grew, and the initial growth was symmetric into a, a few cells and ultimately into a zygote, and then you started getting arms and a head. The symmetry broke. Symmetry breaking is the foundation of life. And it goes much deeper than biology. Now, if you look at patterns, even in the software world, which is taking the cue from Alexander, who talked about patterns as configurations of broken symmetry, the great patterns in the software world break symmetry. Here's one from Northern Telecom called half object plus protocol. Is phone call an object? So I'm making a phone call from here to Enschede. Where's the call object, here or in Enschede? And now I add a third party to the call from Hilversum. Where's the call object? And now I go on hook, and the call object is with me. No. We split the symmetry of the call object in telecom so that there's an appearance of it on every one of these switches. We break the symmetry. This is how great object-oriented design happens. It breaks symmetry, and to do this, we cannot use standard class-oriented design. And the domains that we come up with are going to end up having very intricate runtime structure that's different than the static structure that we tend to find in classes that tend to precipitate from our domain models in a simple way. Now, this goes very, very deep. I mean, initially, there was a big breaking of symmetry when there was a bunch of matter and antimatter in the universe, and something went wrong, and kind of all the antimatter went and hid somewhere. And what we're left with is matter. So this is the reason that anything exists, is that symmetry originally broke in physics. So physics isn't about F equals ma. I mean, that's the superficial, programming in primitive C++ or programming in Java kind of physics of software. The real physics of software is emergent, complex, or chaotic, and has to do with modeling the real structures of business, which involve humans that are among the most chaotic individuals on the planet. Nothing symmetric about it. But we pretend there's symmetry in it, and what happens? Now we end up trying to pound a square peg into a round hole, and we get more complexity. And it's called accidental complexity, because we're carving the system with the wrong knife. I was at a little seminar yesterday, talking in one of these little analysis sessions, and they have a pre-designated library of kinds of relationships between domains. And it includes things like relation in the database sense. And I said, when does someone who does machine maintenance ever talk about the relation between this machine and this machine? It's a cable, for crying out loud. It's not a relation. Relation is nerd terminology. So they have a fixed set of relations. That isn't domain analysis. Domain analysis is listening to your user's vocabulary and building a geometry around the symmetries and broken symmetries that they express. And this is your big contribution, which is getting this vocabulary right. Okay, so we start there, but then we can't take it to a total classification. And having a pre-designated geometry. How many of you do object-oriented analysis? I mean, what in the hell does that mean? You have an object-shaped knife and you're going to be looking for objects in your customer's vocabulary? There are no objects in nature. They're artifices, they're inventions of the human mind that we impose on nature in order to understand it in a system one kind of way. There's no objects in nature. How many objects are you? One. All right. So, this is one of the pictures from CERN that relates to the study of the, the Hadron Super Collider, where they're discovering the so-called God particle. So, given this classification of systems and how we think about and talk about systems and what the structure of the real world is, whether it's, something going on in a bubble chamber, or whether it's a zygote developing in the mother's womb, or whether it's a banking system or a telecom system or a flight control system, the world is not hierarchical. It's complex. So DDD is good for simple and, I think, complicated problems out of the box. Think hierarchy, either top-down or bottom-up. I don't really care. De Bruyl's law says that complexity is proportional to the number of distinct, meaningful hierarchies on a system. Now, I come from telecom, and we build switches. They're pretty complex systems. Hundreds of millions of lines of code, hundreds of processors, thousands of developers at dozens of sites, and they can have 3 seconds of downtime a year for all reasons, including the installation of new software. Pretty tough problem. And we can do kind of top-down thinking about them, top-down analysis. They have a call processing top, making calls, call forwarding, call waiting, three-way calling. They have a maintenance top, how do I install new software? They have a diagnostics top, how do I diagnose the components? They have a system integrity top, it's the kind of things the security guys were talking about. I just came from a meeting with the security guys, which, by the way, is more interesting than this talk is. If someone wants to go to it, they're still meeting upstairs. But they're going to be breaking symmetry, and putting a lot of things in place from a whole other top. Their top is a security top. Complexity is proportional to the number of distinct, meaningful tops of a system. And in domain analysis, you pick one, we call it a domain, or usually the domain, when in fact the system is usually living in multiple domains and they're not disjoint. That line of code is both in the system integrity domain, the maintenance domain, and the call processing domain. It's not hierarchical. So our experience is that domain analysis was a great starting point. We did a lot of work in the software production research department of taking domain analysis all the way through domain-driven design and application-specific languages. And these languages would work well for 1 or 2 years until the symmetry in the domain broke and we got evolution in the understanding of the domain. Now we had committed to a language and to thousands of lines of code written into that language, all of which were invalid under the new domain model. And so it became very, very brittle. I think what most of you are doing, and which does work, is that domain analysis really, really gives you good insight into building the vocabulary, into how things relate to each other, because you have to understand the business. And this is why I like Vaughn's talk here this morning. He says, we need coders who aren't just coding. I mean, they need to be invested in understanding the business. Richard Paul Gabriel is a friend of mine. He was founder and CEO of Lucid. They did Lisp stuff. He said every one of his programmers could read a balance sheet better than an accountant could, because they were invested in supporting the business and understanding the business models. They didn't need to do domain analysis. It was part of their blood for what they were doing. They understood the business. So our experience is that the way that domain analysis works, not domain-driven design, we never had any really great experiences with that. But domain analysis can give you the insight to write a great program in C. And just understand, kind of informally, what are the right shapes? What are the right modules? How do things fit together? But we tend to think hierarchically. I mean, here's a picture from Vaughn's talk this morning, that I just took this morning. And he starts by saying there's this bad thing called big ball of mud. And yeah, it's a bad thing. And Brian Foote and I fought for years. We didn't speak for years, in fact, when he came up with this idea. I said, this isn't what patterns are about. But I did think he had a brilliant insight, and this is how most systems are built, because the forces that people face are artificial. And so we're told break them down. Well, yes, but it's not a hierarchy. And I mean, very explicitly in Vaughn's talk, he showed this as a hierarchy, described it as a hierarchy, and this is what I've been seeing here for the past 4 days, and for the past many years as I've been looking at what's coming out of this community, is that they're all hierarchical. And the problem is you'll get a requirements change that comes along. And by the way, these don't come from an understanding of the requirements. Domain analysis has nothing to do with requirements. If I'm building a telecom system, I don't need to go through all the use cases or the 10,000 deliverable features that we could configure in that. I just know what the parts of a telecom system are. That is domain knowledge. It isn't about taking the use cases to get an understanding of the structure. Because the use cases are 1,000,000 times more than what you're going to have at hand in the beginning. You can't get enough information to make a statistically significant design from it. You have to go with your gut, your hara, our architects in AT&T were people with 60 years of experience, not 60 years old. 60 years with the company. I mean, they knew stuff. And it went beyond just kind of this simple Cartesian divide and conquer. I mean, this all goes back to Descartes in his early years, when he wrote his early stuff. You read his stuff in his later years, and he kind of recants it. So, all of our citing of the scientific method or the Cartesian method, which is based on hierarchy, is a very mature misunderstanding that Descartes had early in his life. Go read his later stuff. It's not hierarchical. It's not divide and conquer. He starts sounding a whole lot more like Blaise Pascal. No architecture perfectly encapsulates change, so go with the best option. I have heard the word coupling so many times here in the past many days. And I heard coupling is bad in the past 2 talks. Let's say we could drive coupling to 0. None of the objects talk to any of the other objects. It's not a system. It's just a bag of objects. Adele Goldberg, who published her Smalltalk book, says, it doesn't happen in the objects, it happens between the objects, between the domains. That's where the action is. It's when 2 objects get together in a community to do something that I start to understand the business repercussions. It's not an individual object. It comes from an individual domain. And so this artificial pursuit of encapsulation is another source of accidental complexity because we abstract. What's abstraction means? Abstraction means to throw away some information in the interest of focusing on some other information that we're interested in at the moment. Someone said this morning, there is no definition of abstraction. I'm sorry, that's a dictionary definition, and I can find it in several computer science books. It's well understood. And it means throwing away information. We need every bit of information we can get. We don't abstract, we compress. I studied French literature and French poetry for many years, especially 19th century. Rimbaud, Verlaine. Is poetry abstract? No. Why is poetry different than prose? Why is architecture just different than ordinary code? It's compressed. Every word means more in context than it does in ordinary French. This is what we're looking for in architecture, is this compression, not abstraction. So, DDD can be a good option to get you started, but then we need to look at all of these axes of symmetry. Object orientation is just one very constrained DDD approach with limited dimensions of commonality and parameterized variation, which is what very common theme in most of the domain analysis literature, which is commonality and variability analysis. This is called CVA or CVS, which again, I haven't heard a word about in this community, but there's probably many more papers in the domain-driven design area published on that than the total number of papers published out of this community. And it really, really works. So mature complex domains, like aerospace, telecom, and finance, patterns are even a better option because now I'm starting to move almost to the border of that chaotic domain, to the very edge of the complex domain, where I need to deal with things in the telecom system like recovering from undetectable double-bit memory parity errors caused by an alpha particle flipping a bit of memory. We need to recover from those things in a class 5 switch. This is beyond complex. So tools and methods can help, but only with the bookkeeping. I'm kind of an Agile guy, and the Agile Manifesto says, something about working software over comprehensive documentation. Does it say don't do documentation? Well, no, it doesn't. We write for 2 reasons. One is to communicate, and the other is to remember. To a first approximation in Agile, we never use documentation to communicate. It's face-to-face. And again, Vaughn said this morning. And it's so good to find someone else who has a common sense view of Jira. Jira sucks. All right. This is all about thinking. And we want the tools to solve it for us. And by tools, I mean things like DDD, as well as, the out-of-the-box, case tools that we buy. No. This is just hard work. The best tools are domain expertise on the teams and effective communication. And you've heard these themes before, in Vaughn's talk and Liv's talk. It's all about people. In the end, that software is interacting with people. And what is object-oriented programming? You all said you're object-oriented programmers. What is an object? Alan Kay's vision of an object is that it's an operational model of a problem-solving ability in the mind of a child, and he was building educational software to help children learn. It should reflect your mental model of some phenomenon. And it's going to be in the code, it'll be in the interface, and it will be in your mind. I'm working with Trygve Renskog right now, who invented ModelViewController. What's on the screen is just a way for me to access what's in the memory of the machine. I mean, in talking to you right now, I love to be able to directly manipulate your neurons, but it'd be really messy. So I work through this interface. And that's what ModelViewController is. Okay? Now, I'll maybe say a few words about DCI, which is going to just add one other axis of symmetry, and it splits the symmetry into what the system is and what the system does. And so we're going to look at kind of form versus function. But then this begs some other questions like, does function have form? And Liv, in her talk yesterday, was talking about, in French and in Flemish and in English, how we render all these phrases and the fact that phrases map onto, boxes and shapes and containers and things like this. To the Japanese, it's entirely different. To the Japanese, time has shape, and it's indistinguishable kind of from geometric shape. They have a concept called ma, which is sometimes translated space-time, where time and space go together. Now, they would understand domain modeling of the dynamics of a system. So I've been doing a lot of work with them. And again, I think we're kind of caught in Western culture, which is all a footnote to Descartes, which is a footnote to Plato. And we tend to, from the point of view of simplifying things, do this system one thinking. System diagrams are usually two-dimensional and are optimized for representing symmetric solutions. So this isn't about diagrams. The code is the design. Kevlin Henney. The code is the design. And I better have an architecture language like C++ that can express broken symmetries. How do I express my domain? In abstract base classes. Now, if there's something that's a relationship that cannot be expressed by the features of the language, yeah, I'll use documentation. I mean, sometimes we need to remember these things. But the code is the design in the end. And intermediate artifacts cannot express the level of complexity except in an informal way. The blueprint isn't the architecture. So all you people who said you were patterns people, I mean, Alexander never does a blueprint because he knows the blueprint isn't the architecture. The blueprint is full of misinformation. It misguides the client into what we're going to build. And reuse makes things worse by introducing yet another axis of symmetry. And by the way, it's a hard one to get right. I'm from Denmark. We had a physicist named Niels Bohr, and he said, be careful about predicting things, particularly if they involve the future. So it's really hard to predict this. And I mean, this has been kind of the holy grail, especially in the 1980s. Contextualization is everything. And so you're going to say, I'm going to make a reusable list. And the C++ people made the standard template library, and they have a reusable list. It's totally useless in telecom because it's not auditable. It doesn't maintain its own links. There's no redundant backlink information to be able to recover the list in case something gets corrupted. Reuse is a matter of context. So I mean, commodity reuse is okay. You know, you're going to reuse something that's been, you know, tested by 1 million people, used by 1 million people, like Linux or a compiler. That's commodity reuse. That has value. But to try to design for reuse, there's a lot of literature that says this is folly. And a lot of it, read the literature by Will Trace, T-R-A-C-Z, who says that you don't design for reuse. You do good design. And reuse is a consequence of good design, a potential consequence of good design. So the repercussions here is you probably need to express several architectures for a complex system. And Conway doesn't live in the architecture, but in the deliverables. Because it's the deliverables that are driving the business. And these are different every sprint. A new set of PBIs that you can't foresee. If you can foresee them, it's a fixed cost, fixed scope project, right? And the reason we're agile is because we can't foresee these and we give ourselves permission to change them. This is how we make money. So the primary cross-cutting I see is feature versus function. I was like 12 or 100 others, who knows. And so we've tried to solve this with DCI. So, I mean, systems have a feature top and a domain top and a bunch of others. And each one of these covers 100% of the code. Each piece of code in a library is there to support some feature. If it's not, take it out. And it's there to support some domain model. If it's not, take it out. And we need to weave these two perspectives together. And there have been a lot of past attempts at this. Aspect-oriented design, reflection, multiple inheritance, dependency injection, and none of them really solve the problem. They're like the 6 wise men and the elephant, around the edge of the elephant, trying to solve this. So in this DCI paradigm, we're going to be able to reason about the dynamics of object networks. I mean, the architecture of a system doesn't exist in your DDD documents. Those are the blueprints. The architecture exists at runtime as a connection of interacting objects. That's the architecture of your system. The other stuff is just the blueprints for it. And what we're going to do is focus on that architecture because that's the one the end user is interacting with and has to match their mental model and serve their needs. So we're going to reason both about kind of the DDD concerns and the deliverables, that is, things like the use cases, at the same time in the code. So, I mean, usually we'll have a domain like text buffer. And the usual wisdom in DDD is that if an object does play in several domains, we add methods to its class for each of the domains it participates in. And these methods add up and up and up and up, and we end up with fat interfaces. So I'm building an editor. I have a text buffer, and it has domain properties. You know, it knows how many characters it has. It knows the top line in the buffer. If it's page, it knows how many lines it has. Spell check. Is that something I do to text buffers? Well, kind of. I mean, spell check kind of belongs between dictionary and controller and text buffer, right? And maybe I can spell check a selection. So now I'm going to do responsibility-driven design based on my domain analysis. It gave me a text buffer and a dictionary and a controller, and I'm going to implement spell check. Where does it end up? Well, of course, here. How many of you can go into your code and draw a circle around the code for your use case? How many of you can go in your system and draw a circle around the code for a domain? We don't sell domains. We sell use cases. No one buys domains. No one buys classes. We buy use cases. That's what we sell. Why aren't we focusing in our architectures where the value is? We're focusing on the cost. Now, that's a good thing. We can reduce costs with a good domain analysis, but it doesn't increase revenues. We increase revenues by focusing on the use cases. This is where the money is. So in DCI, we have a bunch of objects, and you know, A use case can come along on these objects, first of all on this one, then it goes to this one, then this one. That's the blue use case. And there's a green use case that starts here, and terminates here. Then there's a red use case that starts in this object, and then goes to this object, and then it goes to, wait. Well, one of those objects. I guess it depends what instance of the use case is. I'm not going to understand this by understanding the objects. I understand this by understanding the use case. And I want to be able to reason about this without reasoning about the individual objects or classes. So, well, that wasn't cool. Okay. Blue, green, red. So try this again. There we go. I lift these out of the objects as a collection of interactions between roles. Roles are a new concept. They kind of smell like Java interfaces, except they can dynamically attach themselves to objects. And then I make these full first-class citizens that look kind of like classes, but they're an encapsulated use case. This is the form of function. During runtime, objects will be assigned to play each of these roles. It's like hooking up Neo to the matrix and giving that object some information that enables it to do something it couldn't do before. Then lights, camera, action. Each of these actors has read its script. They just perform the script, and they're ready for the next scene. So this has been a quick 1-hour tour of what's probably a full, master's level or PhD level graduate course in computer science. But just to get you thinking at the level of some of the formalisms that underlie the concepts that we use every day. And I know this is one of the few formal talks at this conference. I'm heartened to see so many people. I was expecting 5 people or something like that. So I was honestly thinking of staying upstairs. But software development is complex. It's not just complicated. It's complex, and sometimes it's chaotic in advanced systems because there's multiple orthogonal dimensions of symmetry. So these hierarchical or methodical or reductionist or linear approaches only work to a certain degree. They work good enough that we get the first release out. But then maintenance kills us. And this was the whole purpose originally of domain analysis, was to support evolution in the long term by getting the right parameters of variation set up in the beginning. The other thing that I could have spent a whole day talking about here is we need to get time into the architecture as a full first-class citizen. So far we have these very lazy two-dimensional pictures of what is largely spatial geometry, of thinking of the structure of how things lay in memory of their data. We need to get the structure of time into our architectures because that's what we sell. That's the human mental model. That's what K's idea of objects was all about. And this is what DCI was about, which I gave a tutorial on here the other day, which is now starting to see some broad industrial use. So that's it. I have 2 minutes for questions, or as long as you want to go. There's a coffee break afterwards, but when this clock goes to 2 minutes, I'll say I'm formally done, and you can go get coffee. But I'll stick around if there are other questions. Any questions?
So I find it a very interesting talk, and you talk a lot about objects, and I recognize a lot of the problems that you sketch here. What's your opinion on software that's based, say, on, for example, the actor model?
Well, the actor model is a good start. And I mean, it's a lot like the self-programming language. Basically supports the actor model together with a little bit of, being able to tweak objects and change the frames in them. And Carl Hewitt was a genius. How many of you have met Carl? It's like his mother dresses him funny. He always has these very strange, colorful clothes on. But the actor model tends to be more about time and less about structure. So it's more about having an independent timeline. Now, I have not studied that in depth because we don't have good solutions for that yet. Oh, and I have built asynchronous parallel systems. I mean, I understand synchronization and all of these things, but just we don't have good models for this that map onto human mental models. And there's very little in human mental models that works this way, consciously. The right brain works this way, but it's in the unconscious. Massive parallelism in the right brain. But the left brain, which is what programs, is analytic, and there's only one of you at a time, unless you're schizophrenic. And this is what in psychology is called the locus of attention. And your sequence will follow one timeline. So it's not clear to me that this is a terribly fruitful area of pursuit in the modeling area. It may be in the technology area, you know, if you're getting performance or something, but that's not my interest. And that's kind of the main thing in actors. Now, there's some other things there in terms of encapsulation and autonomy that I think are worth paying attention to. But the main concern there is how we treat time and parallelism in a way that does not map onto human mental models. Other questions? 7 seconds. 6, 5.
Well, I'll just say, thank you for the
Thank
talk.
you very much.
No. That's for you to say. No, I'm saying, just saying thank you because it's, I've never been one for like, oh, let's all sit around and tell each other how wonderful we are and feel good and lose track of, the stuff we're trying to do is very hard stuff. And
Yep.
without shaking it up with a skeptical, critical view, fairly often, it's easy to build up a lot of dead wood, get very complacent. So,
Yeah, and by the way, I love this guy. I mean, we owe a lot to him, if for nothing else, and then getting this idea out there for building a shared vocabulary. And just, I'm sad we haven't had a time to sit down and really process this stuff this week. Or maybe I'll just have to come and visit you. I don't know. But I think there could be a lot of power into what you and I could come up collectively of some compromise or shared model or set of orthogonal models that would complement each other. I really think so.
So that's very interesting, and of course a very huge topic, which probably more than we can do in a minute and 21 seconds. So, oh wait, that's counting up. But
it's counting up.
Yeah. But very interesting, and so we'll talk more.
We'll talk more. Thank you very much. Coffee out there.